Let's pick up where we left off. We were talking about all kinds of electrophiles adding to CC double bonds, bromine, chlorine, hydrohalogen acids. We ended up talking about hydroboration reaction. It's a concerted kind of a 2+2, you call it a cycloaddition. It's not paracyclic, but it leads directly to addition of borane, typically to the less substituted position of a CC double bond. And so let's go ahead and talk about the follow-up to hydroboration. In most cases in synthesis, you'll end up oxidizing that boron-carbon bond. And so let's go ahead and talk about the process of migratory displacements. And I'll start off by talking about hydroboration of a natural product called pinene. So if you go to the hardware store and you buy turpentine, it's used as a solvent. This is one of the major components in that solvent. It's this fancy looking chiral molecule. So imagine using that as a solvent to dissolve grease. If you expose that to borane, or in this case diborane, remember that dissociates to give BH3, you can hydroborate across this double bond. And the product of that reaction gives you the borane at the less substituted position. Remember that the boron and the hydrogen add syn to each other. They add from the same face of the molecule. So if the borane is adding away from, let me try to draw some stereochemistry here. If the borane is adding to the face away from this bulky quaternary center, then you would want the borane to be on top and not on the bottom with that bulky center. So let me draw this Br2, the boron-carbon bond on the top face, and I'll draw the hydrogen atom on the same face that gets added. So that's the syn addition of H and boron. Now you typically don't want boron on there. You can't expose that to some sort of an aqueous workup or do anything good with that. Typically you want to get rid of that carbon-boron bond or use it somehow. And one of the most typical procedures is to oxidatively remove that boron-carbon bond. And typically the conditions are drawn like this, and I'll speak to that in a second. And the important point behind these conditions is that they stereospecifically replace the boron with an oxygen atom. If you had boron up, you will end up with a hydroxyl group up. If you had boron down, you will get a hydroxyl group pointing down. And so that's what makes this procedure so useful. Okay, so let's talk about this, this process of oxidizing this boron-carbon bond. I don't really, I didn't mean to draw up that sodium hydroxide and hydrogen peroxide. Really the whole point of that combination that you always see drawn is that you're trying to make a hydroperoxide anion. So I want to start off with a sort of example of you could have made this through hydroboration using a deuterated borane reagent. It would add deuterium and boron from the same side. This puts a stereogenic center here so you can track what's happening to that boron-carbon bond. And if you treat this with hydroperoxide anion, again, that's the whole point of adding sodium hydroxide to hydrogen peroxide. You can't buy sodium hydroperoxide. You make it by mixing base with hydrogen peroxide. This creates a very nucleophilic peroxide anion, and so as you might imagine, that comes in and adds to this empty p orbital of boron. That boron would love something to add in there, and hydroperoxy anions have that alpha effect as a nucleophile, and so when that adds in, we now have this hydroperoxy group sticking off of this boron, and now it's a boronate. There's a negative charge on boron. That means all the bonds to boron are nucleophilic. Anything attached to this becomes more nucleophilic. And so you can imagine that as this bond here, this boron-carbon bond, becomes more nucleophilic, it's now able to break the weak part of the molecule, and that's the weak oxygen-oxygen bond. It's easy to break oxygen-oxygen bonds, and look at that bond right there, just ready to push out that hydroxide leaving group. And so that's very facile and very fast. And you can see that we don't change the stereochemistry. Let me draw the H. There's an H at this position going back. We don't change the stereochemistry at this stereogenic center on carbon. That stays exactly the same. We're taking this bond and simply migrating it over. And so the product still retains that stereochemical information that was there in the beginning. And so we now end up with this system that has, and let me bend this boron so it's about in the same place that it used to be, although not exactly. And so now you have hydroxide. Guess what's going to happen next with this hydroxide anion? Right, boron is right there, still wants 8 electrons. It's not going to just sit there. It will come back in and attack. And so you'll get, and now the rest of this stuff doesn't matter. We've already set the stereochemistry. You end up with this other boronate. And this is an equilibrium process. The hydroxide can come in, can get popped back out, can come in, can get popped back out, can come in, can get popped back out. Well, eventually you're going to pop this one out. And that's what leads to release. This is very fast, especially during the aqueous workup, these exchanges of boronates, the exchange of alkoxy groups on boronates. So don't be afraid to pop an alkoxide back out. That's occurring with the hydroxide. It also occurs with the alkoxide. And that's the mechanism for release of your alcohol eventually, initially as an alkoxide. Okay, we have a very tricky reaction that we covered in discussion section yesterday. And so I'll just remind you of that. So I'm going to draw out a substrate that's ready to fragment a bond. So here's a cyclohexyl. I'm drawing a chair with a tosylate leading group on there. And I'm going to fuse on another chair with a double bond right here. I can't draw a perfect chair if I have a double bond in a 6-membered ring. So I'll draw some sort of version that shows a little bit of that distortion. That's not a very well-drawn double bond. Let me make it look more uniform. So if I hydroborate this, it's a decalin type ring system, 2 6-membered rings fused together. You end up seeing hydroboration from both faces. But I'm going to draw the product of hydroboration from the bottom face here. And that particular product, in this particular example, there was a methyl group sticking here. After I hydroborate, I now have 2 6-membered chairs fused together. So that's a trans-decalin. Decalin means 10 carbons, but it's this 2 6-membered rings fused together. So now I have the hydrogen on the bottom face. There used to be a hydrogen atom here. It's still pointing up relative to the boron. And so what this does is it sets this system up with a set of anti-periplanar bonds. I've got this good leading group here, this tosylate right there. There's that carbon-oxygen bond. And anti-periplanar to that carbon-oxygen bond, let me use a different pen color since I've got these glorious pen colors here. So here's that carbon-oxygen bond. Anti-periplanar to that, I have this carbon-carbon bond. And so it's aligned with the antibonding orbital, trying to push that out, but it doesn't have enough oomph to do that. So if we could just make this bond in the center of these 2 rings more nucleophilic, we can now push out the tosylate leaving group. And the way you do that is you add some sort of a nucleophile. In this case, they added sodium hydroxide. And so that added in and gave a boronate intermediate. So here's that boron-carbon bond. And now it's a boronate anion. And now let me redraw these bonds here, these anti-periplanar bonds. So here's the tosylate leaving group. Here's the anti-periplanar carbon-carbon bond. And now here's this nucleophilic boron-carbon bond that's donating into this antibonding orbital, weakening this CC bond. It's more nucleophilic now. That donates into the antibonding orbital for the tosylate, and it pops out, and it fragments to give you a ring system that's otherwise hard to make. This gives you a 10-membered ring, and it's very hard to make 10-membered rings. If you're not good at drawing 10-membered rings, you could just redraw the decalin ring system and then erase the bond in the middle. I'm simply going to leave out that bond. So there was an H pointing down here. I'm going to focus on the relationship between the H and the Me. They're still anti. They were anti before. They're anti in the product. Just make sure when you draw the product that you make sure that those are drawn anti to each other. And over here I had an H pointing up. It's still pointing up. And there was an H pointing down at that bridgehead position. And just make sure you retain that relationship when you draw the product. That doesn't change when you go through that bonding. So that's a good way to make 10-membered rings that are otherwise hard to make, is that boronate fragmentation. Okay, we've got one last type of electrophile other than boron to talk about adding to double bonds. And this is really more, what can you do with a boron-carbon bond? Well, you can make it nucleophilic is what you can do. So this is a process called oxymercuration. When the nucleophile is water, if you do these reactions in water, you get a formation of a carbon-oxygen bond and a carbon-mercury bond. How many of you covered oxymercuration in your undergraduate chemistry courses? Higher, because I want to get a sense for the class. Wow, so over 75% of the class, it used to be that 100% of the class covered oxymercuration, and sometimes people would do oxymercuration labs in organic chemistry labs. Obviously, that's toxic stuff, and they tend not to do that anymore. People tend not to use oxymercuration. There's a radical process for instantly 100% yield removing that worthless carbon-mercury bond. And so what you end up getting in the end, if it's water, if the nucleophile was water, is this. And you get very high regioselectivity in a Markovnikov sense. This used to be a very good way for adding ethers in. It's hard to get ethers to add in efficiently without elimination reactions. So this used to be a very efficient sequence for making oxygen-carbon bonds, even if you're making ether carbon bonds to ether nucleophiles. Sorry, to alcohol nucleophiles. But again, the days of this are waning. So why should you learn this? This is why. Everything that you will have learned with mercury, just think in your head palladium. And this is now the mainstay of organic synthesis. So if you know anything about the chemistry of mercury, apply that thinking to palladium. If I simply substitute PDX2 here, that's called a Wacker oxidation. It gets a little fancier at the end, but it's the same idea. Okay, so how do you think about what's going on here when you have metals and double bonds? These things start off with some sort of a pi complex forming. So typically that would be acetates on mercury for an oxymercuration reaction. This problem that we have is that when you draw this pi complex, we can't, I'll draw my dative bond with a dash. We don't always do that. We can't use that dash dative bond, or even if we draw a solid pi bond, we can't use that for arrow pushing. So we're sort of stuck here. What do we want to do? Do we want to show the structure by drawing the dative bond, or do we want to use arrow pushing to predict reactivity? And so I usually just leave out that dative bond because I want to use arrow pushing to show what's going on. So this dative bond thing causes problems for us. The point is that whenever you have mercury on one face or palladium on one face of a pi system, nucleophiles will tend to want to add from the opposite face. It's just like having an iodonium ion. If you wanted to, in some weird way, think about this, like a metallocyclopropane. I wouldn't be upset. An organometallic chemist would be quick to point out that, well, the bond distances aren't consistent with that. That's okay. So if you want to think about it like this, at least you can now push arrows with this. But you'll offend a lot of, about half of the chemistry community by drawing those sigma bonds there. So when you draw the product of this process of having, and let me put all of these pieces on here. So when you draw the product of this process, and let me come back here and take off one of these groups, because this won't really be electrophilic until we lose one of those groups, typically an acetate. So that's what really and now it starts to look like a protonated epoxide. It starts to look like an iodonium ion. And it explains why, if this is differentially substituted, you get attack at the tertiary center, at the more substituted position, rather than the less substituted position. Just like protonated epoxides, just like bromonium ions, just like iodonium ions, it's all the same idea. So you get attack at the more substituted position, and then you lose the proton here, and that's what eventually leads back to this system. So again, you can use the same thinking to think about reactions of palladium. So let me give you one other type of example that's not exactly, where palladium is a little bit different from mercury in a far more useful sense. And I can't think of where we're going to use it in this first quarter mechanisms class, but it's important to know that palladium can induce additions both syn and anti. So I'm showing you this sort of anti-addition, electrophile on top, nucleophile on the bottom. So you can imagine palladium coordinating to one of the pi bases of that olefin. When it does, you can then get carbopalladation across the face of the olefin, where one of the nucleophiles, in this case it's the aryl group attached to the palladium, gets delivered from the same face. And so I'm not going to draw the pi complex, I'm just going to draw the arrow pushing like this. And so this process of carbopalladation will deliver from the same face both the palladium and the nucleophilic R group, typically aryl. This is the basis for a Heck reaction. And so again, there's a pi complex here that I'm not drawing, just like the pi complex. Mercury doesn't do that. Palladium is great at doing that. And this is the start of a Heck reaction and many other types of reactions. So it's not always anti. You can sometimes get syn delivery, typically with alkyl groups, not with heteroatoms. Heteroatoms typically add anti, but not always. Okay, so that's electrophiles adding to double bonds. And so now we're going to change gears to one class of electrophiles that dominates the field of organic chemistry, and that's carbon-based electrophiles. So let's switch off of bromination, addition of acids, hydroboration, oxymercuration. So a major change in thinking here. Maybe not such a major change in thinking. But let's start thinking about addition of carbocations to CC double bonds. Where the pi bond is the nucleophile, and your electrophile is some kind of carbocation. And so I'll take you back historically to one of the earliest useful examples. So here's a reaction that dates back to 1899. So not even, it's so last millennium, but it's totally relevant. And here's my double bond. Could be any sort of an alkene. I'm taking isobutylene in this case. And if you take formaldehyde and you throw it in, that's not electrophilic enough for this double bond to attack. Formaldehyde is incredibly electrophilic, but it's still not electrophilic enough. You need some sort of a catalytic acid to get this to work. You need to make that aldehyde more like a carbocation. And so you can imagine that if you protonate this, so that now you have an oxonium ion, there's a resonance structure you can draw where that looks just like a carbocation. So I'm not going to draw the carbocation resonance structure. I'm just going to draw this as an oxonium ion with 3 bonds to oxygen. But you get the idea. This is very electrophilic. So now instead of having my double bond attack bromine or HBr or borane, I'm going to have my double bond, my CC double bond, attack an oxocarbenium ion. I can't resist. I've got to draw the resonance structure just so we're all on the same page. So the resonance structure for this looks like this. It's really just a carbocation. So that's the other way to think about that. That's a carbenium, sometimes called an oxocar. So this particular resonance form we call an oxocarbenium ion. Sometimes called oxocarbenium ion, but oxocarbenium. Carbenium means a carbocation where you only have 3 bonds to carbon. This resonance structure, it's the same molecule. We call this an oxonium ion, this resonance structure. It's the same molecule, but again, 3 bonds to oxygen, that's called oxonium. A carbon with only 6 electrons, that's a carbenium ion. And that particular carbenium has a hydroxyl group or an oxygen with lone pairs. Okay, so this is the basis for the Prinz reaction. Let me draw the final product so we can see what's going on. In the original Prinz work, you get 2 types of products, and both of them have new carbon-carbon bonds. So here's the 2 products that Prinz was getting when he studied these reactions. And so what's the origin of these 2 different products? They look kind of different. What happens is you start off by forming, after you add formaldehyde, you get this tertiary carbocation, and there's 2 different fates for this. One fate for this is that water can add in to that carbocation, and that's what gives you this. It's essentially like an SN1 type reaction where water adds into a carbocation. That's how you get a tertiary alcohol. The other product of this results from deprotonation next to that carbocation. That's sort of like an E1 type reaction. So it's not exactly E1, but this is the same pattern of reactivity that you've seen before. Carbocations can diverge to give you either addition of nucleophiles or deprotonation. And so that's why you get 2 different products for this reaction. You know, this Prinz reaction sat around for almost 100 years, nobody really using it. It was like, who would want to use a reaction that gives you mixtures of stuff? That's kind of pathetic. But sometime in the 1980s, people started to catch on that, gee, you know, that looks like a pretty decent way to make carbon-carbon bonds. And so let's see how we can change up the nucleophile to make that a faster reaction. You know, formaldehyde, of course, that's reactive. But not every aldehyde and not every carbonyl group is as reactive as formaldehyde. So let's take a look at a series of some other olefins that can add to oxocarbenium ions, that can add to these kinds of either protonated aldehydes or aldehydes with Lewis acids or some sort of carbenium ion that has an oxygen substituent on there. So what I want to do is I want to take a series of double bonds. Here I've got propene. I'm trying to draw an edge on. Here I've got propene. Let's just think about that as a nucleophile attacking things. And in this particular case, it's not an oxocarbenium ion. It's a carbocation with 2 aryl groups on there. So the numbers I'm giving you are specific for this electrophile. And so if I compare the reactivity of this, of just a simple CC double bond like propene, that's not the most reactive double bond in the world, a terminal olefin. But if I wanted to make that reactive, what I would do is I would put a very long nucleophilic bond, like that one, right next door, an allylsilane. Substantially more reactive. In fact, that's 10,000 times more reactive if I just think about raw reactivity, kinetics in this case. 10,000 times more reactive by having a nucleophilic sigma bond poised and activating that CC double bond. And if I make the bond a little longer, I'm sorry my structures look like my greater than symbols. That's just going to confuse things. Let me use a different pen color here because maybe that'll make it less confusing. So if I wanted to make this more nucleophilic by doing something obvious, I would make that bond longer. And I think I have the, no, I don't have the methyl. All I have is the number for tributylstannane. So trimethylstanyl compounds tend to be way more toxic. Tributylstanyl less toxic. But you've got this longer bond. And so this is now 1,000 times more reactive than the silicon. And so now it's 10 to the 7th more reactive. Allylstannanes are on the order of about 10 million times more reactive than simple olefins. That's the effect of having that carbon-tin bond, that long carbon-tin bond that's souping up that nucleophile. And if I really want to soup that up, let me put an even better one. Now we'll put a metal here. And I don't have palladium or cobalt, or all I've got is the number for iron. But you can imagine the same sort of effect if you switch to other transition metals. That's called a FIP group, so cyclopentadienyl iron dicarbonyl. And this buys you another factor of 10 over tin, which is already very nucleophilic. So even better if you can put some sort of a metal there. If you have some sort of an intermediate in your reaction that has a carbon-palladium or carbon-rhodium bond, you can expect that double bond to be nucleophilic. And I don't have a number for this last one, but my intuition is that it's better than all of these. And what's ironic, it's with a second row atom. Carbon-boron. That bond isn't long. But if you make a boronate out of this, if you add a nucleophile into boron so that it's got a negative charge, that now really soups up the nucleophilicity of this sigma bond. And if that's donating into pi, it makes it a great nucleophile for adding to things like carbocations. Okay, so how do you use this in synthesis? So here's one way that you can use it in synthesis. So what you do is you park a carbocation precursor right here. And here's the precursor. It's an acetal. If you pop out that methoxy group, you now have a carbocation poised next to this carbon. And so let me go ahead and draw a CC double bond there. But if you learned anything from this series up above here, what you learned is that you can really soup this up by making that an allyl-silane. So that carbon-silicon bond is souping up that double bond, making it more reactive. And it doesn't make it more reactive at both carbons, it makes it more reactive at that carbon. So now you need something that's going to pop out the methoxy group and generate a carbocation. And so here's a very common Lewis acid, trimethyl triflate. That's a very aggressive silyl transfer agent. That silicon wants to get off of that triflate and onto a regular oxygen. And here's an oxygen lone pair right here. So I'm not going to draw the mechanism for attack of the lone pairs on silicon. I'm simply going to draw this intermediate where I have this trimethyl silyl group there, which turns that into a good leaving group. And so what that does now is this now acts as a leaving group to give you an oxocarbenium ion. Imagine the lone pairs on this oxygen pushing out that leaving group so that you now generate a carbocation, a carbenium ion right here, 5 atoms away from that nucleophilic allyl-silane. And there's 2 different resonance structures you could draw for this. One resonance structure would be to have the CO double bond, that oxonium ion. I'm drawing the carbocation-like resonance structure. And here we go. We attack with that double bond. And the carbocation that we end up with is a great carbocation. You couldn't have known this. This is why they did this study. They were trying to figure out what kind of stereoselectivity do you get. Turns out that you get mostly this syn isomer. So you get this beta-silyl carbocation where that long carbon-silicon bond, that nucleophilic carbon-silicon bond, is stabilizing that carbocation. And any nucleophile, could be even triflate, could be another oxygen atom, could be another oxygen atom and another substrate. Some nucleophile will come along and attack this and initiate the popping off in 2 steps of that silicon group. So the end product of this, and I don't remember the isomeric ratio for this, but the major product is this syn isomer that you get in this product. And you can't even tell there was ever a silicon there. They were just very clever to install that at the very beginning. Okay, so that's an example of taking this Prinz reaction, this old reaction from the late 1800s, and using it as an effective way to make carbon-carbon bonds. Okay, so let's look at some other variants of this Prinz reaction. I want to caution you. In the early days where people used TMS triflate, if you get even the slightest bit of water, and it's hard to keep out water vapor, you end up getting triflic acid as a byproduct floating around. And that is a much faster agent for activating this to give oxocarbenium ions. it's much faster to transfer protons than to transfer silicon. What they found when they tried to control this using Lewis acids and control stereoselectivity is that triflic acid was doing most of the activation to pop off leaving groups. And the TMS triflate was doing very little of that. So you have to be very careful to remove this, typically by adding ditibutylpyridine to these reactions, if you want to make sure that triflic acid is not the thing that's protonating or that's activating your alkoxy leaving groups. So be careful when you use TMS triflate. So here I'm going to take not an intramolecular example. This is now harder, an intermolecular addition of an allylsilane to some sort of an oxocarbenium ion. And we're going to make that oxocarbenium ion by adding a very powerful oxophilic Lewis acid, titanium tetrachloride, TiCl4. So extremely oxophilic, loves oxygen-titanium bonds. Starts off, you get Lewis acid activation. And so that's how we're generating our carbocation, in effect. I'll draw this Lewis acid complex here. Don't feel like you have to pop off the chlorides. You don't need to pop off the chloride to make sure that this is activated. It's activated just like this. So again, there's a resonance structure I could draw that would look like a carbocation, but I don't need to do that. I can tell that this carbon is now super duper reactive. And so if I have this allylsilane floating around in here, it's going to attack. And when I take these this pi bond away from this carbon, I'm going to end up with a beta-silocarbocation intermediate. That's the whole idea behind this silicon. And I want to make sure I count my carbons here so I don't get mixed up. So here's the carbocation, and there's that trimethyl group, that silicon carbon bond that's stabilizing that carbocation. Now, all kinds of things in this solution could act as a nucleophile to pop off that silicon. Nobody runs a reaction on one molecule. If there is any other molecule floating around in solution that has lone pairs on it, it can now add into this, and then in a second step pop that off to give the electrons to the carbocation. So the end result of this, after some sort of a nucleophilic species picks up the silicon, is that it will redeliver that silicon onto this nucleophilic oxygen atom. And so you end up with this as your product floating around in the reaction mixture. This is what's sitting around before you dump in water to work this up. So you may have this tendency to, God, I don't like that plus and the minus. It's killing me. I have to take off the titanium. No, don't take, just leave it there. Titanium loves oxygen. It's on workup that you lose this. No, that silicon has 4 bonds, so. Yeah, when the nucleophile, yes, sorry, there's 4 steps. Nucleophile adds to silicon. Second step, it breaks the bond. Then the lone pair adds to that silicon species. Then in a 7th step, the NU leaves. So I'm not showing all there's 4 elementary steps in order to take a silicon off of here and then re-deliver it onto that oxygen atom. So the end result of this, after you dump in water, is that silyl ether doesn't just stick around. It gets hydrolyzed. So what you really isolate out of this is just the free homoallylic alcohol. It's not allylic. It would be allylic if the OH was here. It's homoallylic. There's 1 extra carbon other than being allylic. Okay, so this is a super common version of how to make carbon-carbon bonds. And if you're throwing in, obviously that's not very interesting in today's world of synthesis. You want to control the stereochemistry. But if you put chiral ligands on titanium, you can get very high levels of enantioselation. You can control which face of the carbonyl the allylsilane adds to. Okay, so what are the common Lewis acids? Of course, titanium tetrachloride is very powerful. You can have chiral ligands on there to control that. Stannic tetrachloride, very powerful. Boron trifluoride, not quite as powerful, but still a good Lewis acid. And now more commonly, scandium triflate, which has bizarre properties. It even works in water, which has always mystified me. But scandium triflate is another common Lewis acid that's used for these types of reactions. Okay, so there's another version of this reaction that has nothing to do with Lewis acids. If you wanted to make this process faster, one way you could make this process faster that I just showed you is to use a Lewis acid. You make this electrophile better. And of course, that leads to a fast reaction that occurs at -78. But the other way to make this faster is to make this even more nucleophilic. So how do you make an allylsilane more nucleophilic? If I just take an allylsilane and I throw that in with an aldehyde, it won't react. If I add a Lewis acid, I can get the carbonyl to be more reactive. But there's another way to do that, and that's to add tetrabutylammonium fluoride, a fluoride anion source. And when a fluoride anion, which loves silicon, attacks that carbon-silicon bond, you end up with a more nucleophilic carbon-silicon bond. And if that carbon-silicon bond is more nucleophilic, it's donating more into pi star and amping up the nucleophilicity of that double bond. This is now a more reactive, more nucleophilic nucleophile. And so that double bond is more nucleophilic, and it can now attack that aldehyde. Now, you can even do these reactions with catalytic amounts of fluoride anion. You don't need stoichiometric amounts of fluoride anion. And you couldn't have guessed this. I don't think you could have guessed that you could have gotten away with catalytic amounts of fluoride anion. There's an equilibrium in this solution. A silicon-fluorine bond is more stable than an oxygen-silicon bond. And I'm not going to draw the mechanism for silyl exchange. But there's an equilibrium here. And if you only threw in a catalytic amount of fluoride, the fluoride that's released in this equilibrium process can come back in and reinitiate another cycle. So the end product of this reaction is this, if you use catalytic amounts of fluoride. Yeah?
On the first step, is the carbon-silicon bond donating, would that, for air fission, would that donate into there first?
Say that again?
So would that donate into like the pi star bond, and then that would attack the...
Yeah, when this is, if you have some sort of a system like this with a fluoride here, so that's a siliconate, that long nucleophilic bond is donating into pi star, and the overall system becomes more nucleophilic. The pi orbital becomes more nucleophilic. There's a more nucleophilic. How would I draw it? Let me see if I can figure out how to draw this while I'm standing at the board. So if I've got some sort of a nucleophilic orbital, and I'll call this a sigma bond for carbon-silicon minus. I don't know if you can see that in the back, but I've got a sigma bond here that's very nucleophilic. That's this bond right here. And if it's interacting with some sort of I'm running out of room here, a pi star orbital for that CC bond, I'm going to get two new orbitals out. So I'm going to get two new orbitals out of this system. I'm going to get some sort of a new pi CC thing. And I have to make sure I end up with the right number of electrons. And I guess that's only showing that, what am I showing? I'm going to get some sort of a pi. I can't do this right now. Let me stop. I'm going to end up with another set of orbitals. It's going to make the pi bond. Here's what I'm losing. There's 4 electrons here, 2 here, and I'm only accounting for 2 of the electrons in my system. Yeah?
Do you want us to actually show that silicon, the nucleophilic silicon showing like donation for the first step?
So in other words, should I, if I take these electrons and I move them over, then the carbon-silicon bond has to be moved over here in the next structure. So don't. Yeah. If I draw an arrow going like this, then I have to move the silicon over. And that's not what you get. You don't get that. You end up with a beta. You should draw it as a beta silyl carbocation. I'll come back and show you how to do this in discussion section. But I have to account for 2 different filled orbitals, one here and one here. So I have to somehow mix a system with 4 electrons. And I'll deal with that. But you end up, by donating into pi star, you make pi more nucleophilic, is the bottom line. OK, so you can see this idea over and over. We can make the double bond more nucleophilic, or we can make the electrophile more electrophilic. And so let's extend that to boron. And once again, we're going to talk about acetal precursors. So here's an acetal. Anytime I see an acetal, the electrons on one oxygen are trying to push out the other alkoxy group. And so there's this tug of war. And so you can take allyl boronates. In this particular case, I'm taking, let me redraw my parentheses here. I'm taking a boron compound that has 3 allyl groups on it. So you can make alloborane from allogrignard and trimethoxyborane. If I add butyllithium to this kind of a triallylborane thing, it now becomes an 8 complex. And so now those allyl groups are more nucleophilic. And what you could not have guessed, so of course this isn't going to react with this. It's not going to do an SN2 reaction. If you stirred those 2 species together, so if you made this boronate in solution and stirred it with an acetal, nothing would happen. It would just sit there. It's not until you add some sort of a Lewis acid, an oxophilic Lewis acid. And here's this TMS triflate again. A Lewis acid that doesn't want to add to these CC pi bonds, even though they're nucleophilic, but loves adding to oxygen lone pairs. So now this siliconate will initiate this process where the silyl triflate silylates, turns this into a good leading group, and now the lone pairs can push that out to make my oxocarbenium ion, or in this particular resonance structure, I'm drawing the oxonium resonance structure. And I'm not going to draw all the things attached to boron. The important part is it's a boronate with a negative charge. So now I've got a fantastic electrophile. I've got a fantastic nucleophile. And even though it's intermolecular, this reaction is still very fast and goes at -78. And then you lose the borane in a second mechanistic step. Okay, so you don't see people use that very often, this version of the, again, these are all variants of the Prinz reaction. You're basically taking something like a protonated aldehyde and adding it to a CC double bond. And so here's the most sophisticated and clever application of the Prinz reaction. The idea is something like this. The idea is, you know, if I have a borane reagent and I want to make that nucleophilic, I need to add some sort of a lone pair into that. And so why don't I simply use the lone pair that's here on oxygen of an aldehyde? It's there. Why not use that? So if I take some sort of borane reagent like this and I mix it together, if boron is a Lewis acid, why don't the lone pairs simply add into that? And they exactly do that. It's like magic. When you do this, this now becomes more electrophilic. But look what happens to the boron at the same time. Now, the allyl system is more nucleophilic. This is more electrophilic. This is more nucleophilic. To start off, this is not nucleophilic at all. There's actually an empty p orbital over here. So you start off with something that's not really very electrophilic, something that's not very nucleophilic, and you've totally changed the character. You couldn't stop this from adding in if you wanted to. It's now super duper accelerated. Even if the concentration of this is only 1 out of every 10 billion molecules, this is so much more reactive than these that you never have nucleophiles coming in an intermolecular fashion. They pre-complex before you form C-C bonds. And so the product of this reaction now has a new carbon-carbon bond. And what's key behind these kinds of reactions and makes them super important in synthesis is that they always involve chair-like transition states. And when things have chair-like transition states, you can predict stereochemical outcome as long as you know that big groups like to occupy equatorial positions in chairs. I'll go ahead and I'll just start off by drawing a chair, and then I'll fix some of the positions here. So let's start by drawing a chair with an axial and an equatorial substituent there, and I'll make that my aldehyde group. So if I want to correctly draw a chair-like transition state, here's my aldehyde that I had. And if there's an R group on the aldehyde and an H, the R group wants to be equatorial. And so here's my oxygen coordinated to the boron. There it is in back. There's 2 groups on boron. One's axial, one's equatorial. Here's the new bond that I'm making. I'm going to somehow make that a dash bond to indicate that that's a, oh, sorry, wrong bond. That's breaking in the, well, let me just leave that there. It's this bond here. That's the new bond that's forming as you attack. So let me put minus here and plus here. And now here's my alloborane. Here's my allo group. There's 2 substituents out here. In this particular case, it's not very interesting. I've got 2 H's there. That's going to become pyramidal in the transition state. And in the transition state, this is going to become more pyramidal, and one group is going to be more axial and one more equatorial. So you can predict, if you've got 2 different substituents here, issues like stereochemical outcome in these reactions. So chair-like transition states. If you take Chem 205 synthesis, you're going to see basically this reaction in 1,000 different versions.
So, Dave?
Yeah.
So that boron is essentially making the electrophile more electrophilic and the nucleophile more nucleophilic simultaneously?
Yeah, it makes the electrophile more electrophilic, and this carbon-carbon bond is now donating into pi and making the pi more nucleophilic. So again, even if it looks like this, even if it looks like the equilibrium is only 1% to 99%, the small amount of this that's in there will be doing all the work. And any other allo groups that happen to bang into this externally don't do anything. They could bang 1,000,000 times and never react. But if there's even the tiniest fraction of this that's coordinated, it will immediately cyclize. Okay, so let's change from allo. I think you guys could probably extrapolate this in 1,000,000 different ways. Putting long bonds on allo groups or 8-like bonds on allo groups. Putting different Lewis acids on aldehydes. Okay, let's go ahead and talk about it. And this may look very similar, but it's completely different. Kind of completely different. This is not an allosilane anymore. This is a vinyl silane. The carbon-silicon bond, the silicon is a substituent directly attached to the double bond. And yet you can still get amazing reactivity by treating these with electrophiles. So in this case, I'm going to draw N-iodosuccinimide. I'll draw the structure. I would hope you know N-bromosuccinimide from undergraduate organic chemistry. This is basically like I2. It's just got a nucleophilic leaving group. So you can imagine any nucleophile will attack iodine and pop out a succinimide anion. It's sort of N- species. The end result here, I don't really care about the fate of the succinimide, is that this allows you to substitute silicon with electrophiles, like iodine or bromine. and it's stereo-specific. If you start off, even with this bulky group, insanely bulky group here, if you start off with this cis vinyl silane, you end up with cis, so it's stereo-specific. And that makes it incredibly useful. You can add halogens, carbocations. So let's talk about why you get this retention of stereochemistry. That can't be because it's the more stable of the two isomers, right? The trans isomer ought to be more stable. Actually, we're going to run out of time here, so I'll come back to this. Just hold on to this vinyl silane substitution, and I'll come back to an explanation for why you get stereospecificity, why you get retention of stereochemistry in that substitution.